Yanzhen Xiong, and his talk is about diagonal forms of inclusion matrices of rainbow subsets.
Thank you for the introduction. Yeah, this is my topic, and this is a joint work with Yanzhen Xiong and Yao Wu. This is the outline. First, we begin with the definition of rainbow inclusion matrix, and then with some results about its diagonal form and null design. And finally, we introduce how to relate the rainbow subset to the slice in a grid. So an n-colored set S is a sequence of disjoint non-empty sets S1 to Sn. The type of S is the sequence of the sizes of S1 to Sn. A set X, a subset X, is a rainbow subset of S if this inequality holds. Note that the n-colored set S is just this set, such that every element in it receives one of the n colors. So the S1 is a set of those elements that receive the first color, and so. And a rainbow subset is just in a rainbow subset, every two elements receive different colors. And here are some notations, and all the subsets here are rainbow subsets. So for any rainbow subsets X and Y, we set this matrix WS takes value at the position X and Y. The value is 1 if X is a subset of Y and 0 otherwise. We call this matrix WS the inclusion matrix of S, which is simply the zeta function of the ranked coset 2 to the power S ordered by inclusion relationship. For subsets F and G, the F by G submatrix of the inclusion matrix is called the FG inclusion matrix of S, or simply a rainbow inclusion matrix. For integers, for such integers T and K, we set WS sub TK to be the S choose T by S choose K submatrix of the WS, and we call this the TK inclusion matrix of S. And we set this WS sub less than or equal to TK to be this submatrix of WS, and call it the less than or equal to TK inclusion matrix of S. Let's look at this example. Let S be a 3-colored set of type 2, 2, 2. Then the 1, 2 inclusion matrix of S is this. The rows are indexed by S choose 1, and the columns are indexed by S choose 2. Here, this is what the entry is 1 means that this red one is contained in this red one, blue one. Okay, and its Smith normal form is this matrix. Here is 1, 1, 1, 1, 2. A diagonal matrix is a matrix each row and each column of which contains at most one non-zero entry. An integer matrix is unimodular if it has an integral inverse. Two integer matrices M and N are said to be equivalent if there are unimodal matrices P and Q such that N is P and Q. We say that a matrix D is a diagonal form for M if D is diagonal and M is equivalent to D. And also we need to introduce this one. For each non-negative integer I, let sigma I denote the ith elementary symmetric polynomial as such. And let S be an n-colored set of type A1 to AN. For any K, the size of this set S choose K equals to the sigma K A1 to AN, and it has this decomposition. And here, we write tau I AI to A1 to AN for this sigma I A1 minus 1 to AN minus 1. So here, let S be an n-colored set of all ones type, and TKN be such integers. Wilson proved that the TK inclusion matrix of S is equivalent to a diagonal matrix whose diagonal consists of this value with multiplicity this much for all j from 0 to t. And Frankl showed that the rank of this less than or equal to tk inclusion matrix of S over any field is always this value. In other words, the non-zero invariant factors of the matrix consist of ones with multiplicity this much. So when the S is of general type A1 to AN, the TK inclusion matrix of S is equivalent to a diagonal matrix whose diagonal consists of this value with multiplicity, this one, with this one. And as for the less than or equal to TK inclusion matrix of S, the only non-zero invariant factor over integers is 1 with multiplicity this much. So we get the diagonal forms for these both two kinds of rainbow inclusion matrices. And so here is a corollary. So we know the rank of these two matrices. So let F be a field of characteristic P, then the rank of this matrix over F is equal to this one. And for any field F, the rank of this matrix over F is equal to this one. So we know their diagonal forms and we know all their ranks. So we can have some discussion about their rank. Assume that L is the number of rows AI that is bigger than 1. Let F be a field of characteristic 0. When T plus K is at most n, then the matrix has 4 row rank over F. If T plus K is bigger than, is greater than or equal to n plus L, then the matrix has 4 column rank over F. The ranked poset 2 to the power S has the full rank property if and only if L is at most 1. Here, full rank property means that this matrix has either full row rank or full column rank over F for any such TK. Here is a question. When S is of general type, is this ranked poset rank unimodal? This means is this sequence unimodal? Okay. Let these two kernels be the right C modules. So here gamma is an integer vector such that here the matrix times the vector is 0. Also here, see. Each non-zero element in this kernel, in this C module, is known as a null TK design on the ranked poset 2 to the power S over Z. So let F be a field of characteristic 0. By the rank results, we know that these two Z modules have the same rank over F. And it follows by definition that this Z module contains this Z module. So these two modules are actually the same. Can we find a basis for it? I need to introduce the definitions of Frankl rank and Frankl set. I shall introduce the definitions with 2 examples. First example is like this. We choose the set K as a subset of this set 1 to 16. We represent this set K with a walk. This walk is in the X or Y coordinate system, and it has consisting of 16 steps. Each step is of length 1. And so we start at the original, and the ith step is to the up if I belongs to K, and is to the right if it's not in K. So here we obtain this walk here. Now, clearly this value is the size of K. And then we consider this line, and we move it from the very top, very up to down, such that it first intersects this walk. So when here, this is where it intersects the walk, and this intersection here, this value is called the Frankl-Graham density of K. And then the length of this line segment is called the Frankl rank of K. With these lines, we may obtain the Frankl set of K is the set of these blue elements. And the size of the Frankl set is the Frankl rank of K. So for this K, we obtain is Frankl rank is 6. Its Frankl set is this set, and then we may obtain the homogeneous polynomial. Note that this blue one comes from the Frankl set of K, and this red one comes from the K, the set K. Then let gamma K be the 0 ± 1 function such that this holds. For example, let us look at the value of gamma K at position K. So K is this one. We can see these red ones. So here x1, x3, 4, 7, 9, 10, 13, 16, and this corresponds to the K. And for this term, its coefficients in this homogeneous polynomial is 1. So the gamma K takes the value 1 at position K. Then we consider the general type. For example, let S be the 7-colored set like this. It's a red, orange, yellow, green, cyan, blue, and purple. For each color, we fix an element like this. We fix the 1 in each color. Then we consider the rainbow subset K here. To get the Frankl rank of K, first we pick out those elements in K that is not fixed. So we get the green 2 here and the blue 2 here. And for the rest of the elements that is fixed, here is a red one, orange one, and the purple one. And we regard it as a subset of this one. What's this? This is the here the blue and the green and blue color are used. So we consider the other 5 colors, and each color choose the fixed element here, and they are ordered in here red, orange, yellow, cyan, and purple this way. So this one is the same as the set 1, 2, 5 as a subset of the blanket 5, and the Frankl rank of this set is 1. So here the Frankl rank of K is 2 + 1 = 3. Also, note that for the Frankl set of K, first for these non-fixed elements here, green 2 and blue 2, we choose the fixed element with the same color. So we got the green one and the blue one. And for this set, since the Frankl set of 1, 2, 5 as a subset of the bracket 5 is 4, is the singleton set 4. So we pick out this the fourth element here, the sign 1 here. So we get the together we get the Frankl set of K, and then we get the homogeneous polynomial. This note that this here green one, blue one, and cyan one here comes from the Frankl set. And the others like green 2, blue 2, purple 1, red 1, and this orange one comes from K. And let gamma K be defined in the same way. So here's the result. Let S be of type be of all one's type. Then for those K subset capital K with Frankl rank at least T plus 1, this gamma K form the basis of the Z module. And it's almost the same when we generalize to when we consider general type. So let S be of general type A1 to AN. And for the K size K rainbow subsets capital K with Frankl rank at least T plus 1, this gamma K form the basis of the Z module. There are some other non-TK designs. We fix an element in each color. For two size K rainbow subsets K and K prime, we define that K prime is smaller than K if K prime can be obtained from K by exchanging some elements from K set minus 1 with the elements in 1 without changing the color. For example, we fix the red one, green one, blue one here. And for this set, we change the red 2 to red 1, we obtain this one. And we change the blue 2 to blue 1, and we get this set. So we have this relationship. For each K size K rainbow subset of S, let sigma K stand for the column of the matrix indexed by K. Then we obtain this linear relation. It gives non-trivial linear relation when this holds. Okay. For any non-TK design in that basis, its minimum support size is 2 to the power T plus 1, and its second minimum support size is 2 to the power T plus 2. For any non-TK design obtained by the non-trivial linear relation in the former page, its minimum support size is 2 to the power T plus 1, and its second minimum support size is 2 to the power T plus 2 minus this T plus 2. With this proposition, we know that for any non-TK design, the minimum support size is 2 to the power T plus 1. Here is a question: what's the second minimum support size of a non-TK design of 2 to the power S over Z? Finally, here we introduce how to relate a rainbow subset to a slice in the grid. So let S be an n-colored set of type A1 to AN. Note that S choose N is nothing but the grid S1 cross to Sn. A grid point set can be regarded as the rainbow subset. This one, X1 to Xn, a set of this. It's an n-colored set of S. It's a size n rainbow subset of S. A subset J1 cross to Jn is called a K slice if we can find K indexes such that for these K indexes, the Ji equals to Si, and for the other indexes, the Ji is singleton set. Every K slice can be regarded as the rainbow subset. This is the set we unite all all the singlet set here. So this is a size n minus k rainbow subset of S. Let us look at this example. Here is a grid. Here is a grid of size 2 times 2 times 2. So this grid point is the red one, green one, blue one. And it's related to this size 3 rainbow subset. And for these two slides, consisting of these 4 points here, we associated with the size 1 rainbow subset. And for this one slice here, we associate with the size 2 rainbow subset. Okay, so let us consider a collapse process. Here, let F be a grid point set. For any grid point X in F, we say that X can be removed from F if there is a one slice of the grid T, such that X is the only element in the intersection of T and F. So here is the question. What is the maximum size of a grid point set in which all points can be sequentially removed? This question is equivalent to this question. What's the maximum size of a unipotent submatrix in this n-1 n inclusion matrix of S? Clearly, to this question, the rank of this matrix is an upper bound to this question, to the answer of this question. And this proposition, this is the key to our work of determining the phylogenetic numbers, or equivalently, the Morel numbers of generalized Hamming graphs. Let us look at this example. Let S be a 3-colored set of type 2, 2, 2. In the 2, 3 inclusion matrix of S, we can find the following submatrix. Here, this is a lower triangular matrix. And every diagonal entry is 1. So we pick all the column indexes of the matrix here, and then it's related to this grid point set consisting of these 7 grid points here. And these 7 points can be sequentially removed in this order from left to right. Note that this matrix lower triangular matrix, so removing order is from left to right. If we find a up triangular matrix, then the removing order is from right to left. Yeah, and that's all for my talk. Thank you for your attention.
Thank you very much. It is really a rainbow talk. Well, I wonder what is the definition of the second minimum support? Maybe I missed this definition. How do you define it?
Which
the
one?
Second minimum support.
Oh, second minimum support.
Yeah.
So like here,
yeah. What is the definition? Well, I know what does it mean, just minimum support, but how do you define the second minimum support?
So apart from those null T design with support 2 to the power T plus 1, the null TK designs may have different supports, and the minimal one is 2 to the power T plus 1, and we are wondering what's the second minimum one.
Yes, yeah. I think any other questions to the speaker?
This question.
Yeah, please, Alexander.
Just terminological question. What is the difference between Smith normal form of the matrix and diagonal form of the matrix introduced in your lecture? So this is Smith normal, yeah. But what is different?
Yeah, this is Smith normal form.
Yeah, but
The Smith normal form is if a diagonal form of the matrix, the non-zero invariant, the non-zero entries in the diagonal can be ordered as D1, D2 to DR, such that the DI is a divisor of the D.
so this Smith
I
normal
plus one.
form.
Then it's the Smith normal form.
But
Yeah.
in diagonal form, you don't need this kind of restriction, yeah? Just any
Yeah.
element.
Yes.
But you need to calculate co-kernel of this matrix, but both are sufficient to calculate the co-kernel of this operator, yeah? This is just direct product of cyclic group staying on diagonal, yeah?
Yeah.
So for your purpose, both are enough. Okay, thank you, I understand.
Okay.
Is there any other questions? Well, if not, then let us thank speaker again. Thank you very much for your interest in Frankl.